recording to see if the audio works. Oh, interesting.
Okay.
Oh, so
okay, I have to redo the thing.
Okay. Yeah. But yeah, today we are resuming our guest presentations, and we have a pleasure to welcome Felix from University of Ghent, and recently he's been working on guidance in diffusion models, and today he will present his latest findings on it. So yeah, the stage is yours.
Okay, yeah, so thanks for having me, guys. So yeah, as you mentioned, my name is Felix. So I'm from Ghent University, and I work on the guidance of diffusion models. And I'm here to talk about our newest work on a concept called feedback guidance. But first of all, I'd like to thank everyone that's been involved in this work, because I think without these, it would have clearly been impossible to reach what we have done. So I would like to thank Florian, Johannes, Thomas, and last but not least, Luca. Okay, but let's get into it. So what will I be discussing today? So first I'll give kind of an introduction into feedback guidance, and especially why we actually thought that feedback guidance was an important thing, and what are the intuitions behind it, basically. Then I'm gonna describe the typical classifier-free guidance algorithm mathematically, and I'll also show some kind of common misconceptions and also a slightly different take on how we think that actually classifier-free guidance might be better understood, let's say. And that will lead us quite naturally to the derivation of our feedback guidance scheme, which I will first describe from a theoretical perspective and then show how it works in practice. And then I'll briefly add a small conclusion to kind of summarize the whole talk and give the main takeaways again. Yeah, if at any point you guys have some remarks or some questions that you feel would fit very nicely, feel free to interrupt. I think it's good if it's interactive as well. You don't need to wait for the end. So just go for it. Just wanted to clear that up. Okay, but so let's start with the intuitions behind our feedback guidance approach. So this is a very typical diffusion diagram where you go from a fully noise distribution at time step, let's say 1, to the noise distribution, or in this case, a bimodal distribution at diffusion time 0. And now the idea during diffusion is that you walk along these stochastic paths and you sample different trajectories. The topic of guidance is really about conditional generation. So in this case, we'll make a distinction between the unconditional distribution, which contains both of these modes, and the conditional distribution, which contains solely the top mode. And in the case of conditional sampling, what you would want to do is to only retrieve this top mode. And okay, now maybe you realize that I have kind of highlighted one part of the region of this graph. And I think you guys are already have an idea of why. And that's because that's a very important region that kind of determines as to when you actually decide towards which mode you're going to go. It's kind of the so-called spontaneous symmetry breaking moments. Like before that, you have no idea to which mode you're going to go. It's essentially completely flat and you don't know towards which mode you're going to go. And afterwards, it's already fully decided. You're already either on the top mode or either in the bottom mode. So it's really at this key moment that actually that decision happens. So that's a very critical window of the diffusion trajectory, especially in terms of what mode you're actually going to end up in, let's say. And now what's guidance about? So guidance, the idea of guidance is that actually the conditional distribution, in most cases, as is the case, for example, with images, is very difficult to learn. It's not really something as this bimodal distribution where it's very easy to classify. It's very difficult to learn this conditional distribution. So it's most likely that your learned distribution is actually slightly erroneous, which means that you kind of need to add some additional conditioning signal. So in this case, that would be some kind of like upward force where you kind of push your samples towards the top mode. You kind of add this bias of telling them, you guys should be going upwards because we're trying to sample the top mode. So that's kind of what you do with guidance. And so the first that came up with this, just apply this constant force with a constant throughout the whole diffusion trajectory, regardless of the trajectory. You just apply this constant force to really make sure that you're going to sample this top mode. That's kind of the main idea. Now, an obvious extension, which took quite some time to actually come up with, so you can see that there's a 4-year difference between these two papers, is that of limited interval guidance, which basically says that actually this guidance, this additional force, you shouldn't apply it throughout the whole trajectory, but you should only focus at these regions where you actually decide towards which modes you're going to go. So towards these symmetry breaking events. That's kind of the idea. You should only focus your guidance there, and there you can apply a stronger force maybe, but really in a limited interval. So that's really, it works very well in practice, and it's a very great and intuitive results in a way. But our idea is actually to go really way beyond that, and is really to step away from this idea of guidance as just a global fixed scheme that you apply regardless of what's going on. Like, our idea is the following. Imagine that you have a trajectory as this yellow curve that actually very early on, you already know that it's going to go to the top mode because it's has such a strong bias. It's so high up in this on this x-axis, for instance, that you already know that you're most likely going to end up in the top mode. Well, the idea is that for these kinds of trajectories, for which the learned conditional is good enough, you should not add any additional guidance because you're already going there. So you have no need of adding this additional force. Whereas imagine that you're along a trajectory which is much more in between, where it's actually unclear towards which mode you're actually going to go, then it might be wise to add just a little bit of guidance to make sure that you sample the top modes. And then if you take this even further and you take an extreme trajectory that even like very late on seems to go towards the wrong mode, then at that point, it's definitely wise to really activate the guidance and to make sure that at that point you really push the trajectory towards the correct mode. So that's kind of like really our idea behind feedback guidance, is really to have not just a global fixed scheme, but really something that kind of understands that guidance only needs to be active if your conditional model is actually really bad. If the conditional model is already good enough, then you probably do not need guidance at all. So that's kind of the basis of our ideas. Okay, so now maybe let's start with a more rigorous explanation. And let's start with classifier-free guidance, which is the prerequisites, if you want. So the idea of classifier-free guidance is to really emphasize the conditional signal. So the idea is that actually the learned conditional is not good enough because it's very difficult to learn such a distribution. So for instance, to illustrate this, I looked at like text to image in a stable diffusion model of an image of a fluffy dog wearing sunglasses. And if you just sample using the conditional score, what you will obtain is an image that looks roughly like a dog. You can see the sunglasses somewhere in there. You can probably recognize a dog, but clearly, if that was the best we could get out of diffusion models, they wouldn't be such a big thing, right? Like they wouldn't be the main thing going on at these machine learning conferences and so on. You really need to get more out of the model to really get state-of-the-art approaches. And so the idea is that you're actually going to apply a decomposition of the score. So you're going to do a linear combination of the conditional and unconditional score to kind of push it even more in the direction of all of these details that are already present in the image. So for instance, here you can clearly recognize that there's some signal of like sunglasses, some signal of fluffy dog, and you really want to emphasize that. And the way you emphasize that is by doing some kind of contrastive objective between the learned conditional and the learned unconditional. And you kind of try to really remove the information about the unconditional distribution to really sharpen only these features that make that image more special, let's say, than just a plain image. So really, you try to kind of emphasize for example, the sunglasses and the fluffiness of the dog, for instance. And if you do that, so that happens through the equation written above with this contrastive objective between the learned conditional score and learned unconditional score. And you add this additional constant called the guidance scale, which is larger than 1 and typically around 7 in the case of text to image. What happens if you sample using these modified marginals? What you get is that you really get these very nice looking images of where now you can clearly recognize the fluffy dog and the sunglasses are very clear. And now you can clearly understand why diffusion models are actually such a thing at these conferences. But really, the main point is that at the marginal level, you're really going to apply this decomposition, this linear combination of the scores, if you want to really emphasize the conditioning signal, which is already somewhat present, but just not good enough. So you really try to strengthen that. Now I'm going to do a small intermezzo. It's not really essential for this talk, but I think I wanted to take the opportunity to say it because I think it's really a common misunderstanding of classifier free guidance, which should definitely be fixed, in my opinion. And the thing is, classify free guidance, for those of you that are familiar with it, it's really often explained as sampling from a lambda sharpened distribution, as they say. And the idea is that you start from this equation of the linear combination of the scores, and if you kind of put it all together, for example, by bringing the lambda into the logarithm as an exponential, and putting these differences of the logarithms as a fraction, and you just squish everything together, you get this equation, which kind of seems to imply that you're sampling from that modified distribution, which if you apply Bayes' rule to this ratio of likelihoods, you get like this classifier likelihood. And so that was the intuition that people first came up with to introduce guidance, actually. And the idea is that you try to sample from a distribution where you make sure that this classifier likelihood, this posterior likelihood, is as close as possible to 1, essentially. Meaning that all the regions that are not really 1 kind of like get washed away, and you really only keep these regions where you really have this very nice fluffy dog with sunglasses. And that's how it's typically explained. But actually, there's a fundamental flaw in this explanation, and that flaw is that in this derivation, I explicitly omitted the subscript t. Actually, here I pretended that this was just something that I applied at the clean image level, but this is really not the case. The classifier free guidance is really something that you apply at the marginal level. At every time step, you apply this linear decomposition. And now, what's the problem with this? Well, the problem is that this does not really commute with the forward process. So that means that if you apply this at the time step t, this decomposition, if you were to have this lambda sharpened distribution at time step t, if you are to forward noise it, so that means applying a convolution to it, you would not end up with having a lambda sharpened distribution at the next time step. So really, you do not follow a valid sequence of lambda sharpened distributions, if you want. And so that's really a fundamental misconception of classifier free guidance. You're really not sampling from this lambda sharpened distribution. What you're really doing is at the marginal level reinforcing the conditioning signal through this contrastive objective. That's really what you're doing, but you're really not at all trying to sample from that distribution. That's not the point. Okay, so that was the small intermezzo. Maybe now let's take a step back and try to find a different view on classifier free guidance, and we're gonna because the idea that we need guidance is that the learned conditional model is not good enough on its own. So let's actually see what we assume that mistake to be. Why is it not good enough on its own? How do we assume that it looks like, actually? And so what we're going to assume is that we're going to assume two things. So first of all, we're going to assume that what we're actually using as a score, using classify free guidance, actually corresponds to the true conditional distribution, because at the end we do get good images. So it's most likely that we try to approximate this true conditional distribution. And the second thing is that we assume the unconditional distribution to be well learned, which kind of makes sense because it actually sees much more unconditional training data, because the difficult thing to have access to are really the labeled images with a prompt and an image itself, whereas like for the unconditional generation, you just need images, which there are plenty of, and it sees that really a lot during training. So it makes sense that this one is well learned. And so here you can see kind of already that there's a dependence between the learned conditional, so in orange, and the true conditional unconditional distribution. So you can just rewrite it as such quite easily. And so here you see that you kind of assume the learned conditional distribution to be a multiplicative mixture of the true objects that you're trying to approximate. And maybe to kind of understand this equation just a bit better, let's look at first the low guidance regime. So that's the regime where the guidance scale is close to 1. Well, when the guidance scale is close to 1, essentially, if you plug in lambda equals to 1 into this equation, what you observe is that the learned conditional is actually just the true conditional distribution, which makes sense. That's why we could use low guidance. We didn't need to apply that much guidance. Our model was already very good on its own. And going to the other extreme, where you really apply high guidance, what you see is that, in fact, in that regime, the learned conditional distribution is much more similar to the unconditional distribution, which is precisely why we had to use such high guidance. So basically, when you say that you need to apply high guidance, what you mean is that you have a very bad conditional model, a very bad learned conditional model. That's really kind of the new interpretation that we propose on guidance scheme. And we think it's much wiser to think about it in that way, in fact.
So maybe can we say that, let's say if we are training on a lot of classes, maybe the model kind of give up in actually trying to use the class information, and it will just give you the kind of non-class specific output, right? Because simply does not have much information concerning a specific class during training, since it's very early sample. Is it a good picture of the?
Yeah, exactly. I think that's kind of the idea that, like, for these very specific classes, for example, in the case of text to image, if you have like a very complex prompt that contains like tons of elements, well, definitely that's not been in the training base. So at that point, the learned model will be way off, just because it hasn't really seen that as often. So it's very difficult for it to actually be well learned for that specific condition. And so in that case, you really need this high guidance, just because your learned distribution of that condition is really way off. And so that's kind of indeed the idea. Whereas like for these more simple prompts, or even the unconditional as kind of the simplest prompt, if you want, the null prompt, there it's really well learned, because it's seen that quite often. So it has a very good idea of what should be going on at that point. I think that's really indeed the main idea. Okay, but so now actually, through this error assumption of a guidance scheme, you can actually come up with very creative ways of defining different errors. Of like, basically you could come up with any different combination of the conditional and unconditional distribution to kind of represent what your learned model has done. And that's precisely what we'll do, and that's how we'll arrive at our feedback guidance. And so the first obvious thing that you try is to see what happens if you have actually an additive mixture of the two. So the idea here is that, I have again this bimodal distribution, with the conditional distribution being only the top mode, let's say, and the unconditional being the two modes. And what we're going to assume our learned conditional model to be is a linear combination of these two. So kind of that learned conditional model has kind of remembered that there is this second mode just because for instance, they're often jointly trained. So we think it's very likely that it has some information about other features that are present in the space. So for instance, imagine if we ask for the image of a bird, it's likely still going to know how to generate trees and things like that. So those things can be interconnected, and makes sense that there's some kind of leakage of information, if you want, from the unconditional to the learned conditional. But this is just an assumption. We're not trying to claim that this is exactly the error of the learned conditional model, right? That's not what we're trying to say. We're just showing that actually you can take a completely different assumption on the error, and that this can still lead to valid equations. And in fact, you could come up with any error assumption here, and like feel free to go ahead and find out your own. And there might definitely be better combinations out there. But here I think the additive. Yes, you had a question?
Yeah, I feel, of course, obviously this is not going to be the true assumption, right? In the sense that the reality of the error is going to be very complex. But I would say that it's a bit more realistic than the multiplicative one. And a basic factor is that the multiplicative one requires this kind of, that the model, while it's badly learned, is still extremely knowledgeable of its low probability region, which is a bit of a catch-22, right? How can you know that? Because basically the leakage is proportional to the probability in a multiplicative case. So you're saying that I don't know what the bird is, but I know exactly that it's not the dog. So that there is not going to be leakage from the dog class. And that's a bit unreasonable, right? Because since you still don't know what the bird is, since the model does not know that prompt well, that zero probability region is not well estimated and cannot enforce this very sharp protection against leakage. So that's my idea of why this is a good model, or this is a better model.
Yeah, exactly. I think the main point here is that we actually give some weight to the zero probability regions. We really kind of assume that our model still knows what's going on in different regions of the space, which is in essence already like a very likely assumption. It's only natural that it kind of still knows what's going on somewhere else, that there's some kind of leakage of that information, which is more represented in an additive error than in a multiplicative error. Okay, but so...
Because it's the argument that if it was multiplicative, if one of the distributions has probability 0, then the result would okay, which is not the case basically. Okay.
Exactly.
Yeah, exactly.
So being said, the model does not know what the true distribution is, but somehow this true distribution has an extremely protective effect in the sense it determines where leakage can happen or not happen. That's quite very reasonable, right?
Yeah. Okay, but so now we've defined our error, but we still need to get back, because at the end of the day, what we want to sample is not this mistaken learned conditional, but we want to sample the true conditional distribution. So we still need to rewrite it as such, which is quite easy. And here again we assume that the unconditional distribution is well learned, which makes sense because it's been seen much more often, as we said. And here in this equation, it also becomes clear what we need to do to reinforce the conditioning signal. We need to remove a bit of the unconditional distribution. So in this figure, it would be removing a bit of the blue line from the orange line to kind of push all of the regions that are not of the condition towards zero probability. That's kind of the idea. So in this way, you can reinforce the conditioning signal in a way similar to what classifier free guidance was doing. Obviously, because we're doing score-based modeling, we want to compute the score function of this object. So we need to take the gradient of the logarithm of this object. So for this, we're going to rewrite it. So first, we're going to apply the chain rule to the logarithm. So that means 1 over the thing, and then the gradient of the thing, let's say. And then we're going to actually artificially reintroduce the logarithms by every time multiplying it in front and then reintroducing the logarithm inside. And here already you can see that you actually obtain a linear combination of these two scores with so of the conditional score and the unconditional score, with as important twist that the parameters of this mixture are functions of the likelihood. So they're not, it's not just a constant, they're really functions of the states, let's say. And then through some very easy maths, you can actually show that you can very easily rewrite it in a way that looks very, very, very similar to the classifier-free guidance case, with as only difference that instead of having a constant guidance scale of lambda regardless of the state, we really have a state time dependent function lambda. So this is really the main point, is that you really, at the end of the day, you obtain an equation very, very similar to classifier-free guidance, with as only twist that you get this time-dependent guidance scale. And now, how does this dynamic guidance scale actually behave? So here I've written it down for you. So it depends on the likelihoods, and you can, by dividing the numerator and denominator by p of x, what you see is that you kind of need to weigh this likelihood ratio of how much more likely am I currently like walking along the conditional model that I'm walking on along the unconditional model, which is kind of nothing else than the posterior likelihood, or like a classifier likelihood, basically. In essence, what you're trying to estimate, I think it's quite clear on this figure, for example, for this yellow line, which is clearly going to the top mode. Essentially, if you're going to look at how much more likely it is to go to the top mode than it is to go to the bottom mode. That's really the point. You really try to evaluate how much more likely it is under the conditional likelihood than it is under the unconditional likelihood. And by knowledge of that, you can really estimate where you're going, kind of what the posterior is. And here in this figure, I've plotted how it looks as a function of this posterior quantity. And you can observe a few things from this. So first of all, there's an asymptotic behavior towards 1 minus pi, which essentially means that as the posterior is going to decrease, so that the model thinks that it's going wrong, it's not, imagine that it's not generating the correct object, so the posterior goes down. At that point, the guidance will kick in. It will really increase drastically until it reaches this 1 minus pi, where it really becomes extremely large, let's say. And so that's kind of the way of, like, if the posterior goes down, the guidance scale goes up, because it thinks that it's actually not generating the condition, so it needs to kick in the guidance. That's the idea. Whereas if the posterior is very large, you just get this guidance scale of 1, which just means applying no guidance, basically. Yeah, now in the maybe a twist is that, yeah, if it's lower, if the posterior is lower than 1 minus pi, what you obtain is actually a negative guidance scale. But in fact, we argue that if you were really in the continuous case, you would really not cross this asymptotic region, just because you would get this very high guidance scale that would really push you back towards higher posterior likelihoods regions. So in fact, but obviously because we discretize it, it could happen potentially. So we add this additional clamping on the posterior, which essentially just boils down to having like a maximal guidance scale value, if you want.
That there is an infinite barrier of potential, right? But then, of course, into discretization, it could.
Exactly. It could. The problem with the discretization is that it might be able to do a jump like that. But in the continuous case, not, because it's an infinite border, right? So it's not really possible.
How should we understand this negativity? Like, is there an intuitive way?
But I think that it's really a it's really not, I think, a physical region. I don't think that it should be ever be sampled, because yeah, in a way you could see it as well also for the additive mixture. So imagine that this could lead to erroneous distributions, right? Like, this still needs to be a valid distribution. So this still also needs to satisfy like some kind of positivity constraints if you like remove too much of it, because pi is a hyperparameter. We don't know pi, right? So we need to estimate pi. And so if you were to remove a bit too much, you might actually end up with non-valid distributions. And we think it's kind of an artifact of that this negative region appear. Like, this pi is really a hyperparameter in a way. But I think it's really not, the point was not to have this discussion about the negative region. It was merely to kind of illustrate that we add this clamping, because I think it's important that people know what we actually implement and what we're doing. And so we have this additional clamping, but I think that really in the continuous case, this should not happen. This should really not be a thing. But obviously we discretize, and that often in diffusion you try to discretize as much as possible, right? You try to minimize the number of function evaluations, which means that really the more scarce the discretization, I think the more this clamping is important, I think.
I had a question. In the last slide, why does the pi get removed?
In which one?
In the first step, when you go to the parameterized version, the pi gets removed.
The 1 over pi, you mean?
But if it's proportional, then
you don't care about
yeah, I wrote it proportional because the thing is we're only interested really in the score function, which involves the gradient of the logarithm, which like all of constants kind of fall out. Because with the logarithm, you get like a plus, and then you have the gradient of a constant, if you want. Obviously, you could, I mean, maybe now you're thinking, yes, but what if this pi is like also state time dependent? Then obviously you could get into those kinds of things, but we really want to make the most simple assumptions and do not want to get into, but clearly you could make some other assumptions that would definitely involve difference.
Pi being time dependent doesn't change anything, right? And in fact, as we do use time dependent pies, as you will tell us later on, right? So if time dependent, it still goes away because this is a gradient.
No, I mean, state time.
Okay. Yeah. So that will be interesting. It will be interesting to think about a situation in which, that will play a factor, and then we need to keep in mind that the formula is going to be slightly different.
Yeah, for sure. I mean, there's really that's I think also really an important takeaway is that this error model really gives you lots of freedom on to come up with new guidance schemes that are really relevant, that make sense. I think it's a much better take on guidance than what's usually described, I think. And it's really, it's just a framework, right? So you can play around with it, and I think you can come up with plenty of nice ideas. Okay, but now most likely, if you're familiar with score-based models, you're going to say, yes, okay, that's very cool, but like in the entire point of score-based modeling is that you do not have access to these likelihoods, but that you only use the score function, and that's enough to actually sample the likelihoods, but that you don't know what the likelihoods are. And in a way, that's true. That's at least what's commonly known. But actually, funnily enough, so we had some work at iClear this year where we refer to dynamic negative guidance of diffusion models. So we use kind of a very similar approach, but for negative guidance. And there we also needed to estimate these densities. And actually, it turns out that when using a stochastic sampler, you can actually get these likelihoods just for free through some kind of actually nice correspondence between the score matching objective and the likelihoods. And so let me kind of give you a hint onto how that comes to be and to how that happens. So what we derive in our paper, there's other works that derives it in a different way. But I'm going to take this approach to illustrate it here, is that we're going to decompose the likelihoods into their Markov chain, so into all of the transition probabilities at every time step, let's say. And then we're going to look at like the log likelihood ratio of this entire Markov chains, of these two Markov chains. And essentially what you find is that that's kind of an iterative object, right? Like at every time step, you just need to add a little value to the Markov chain. Like those are just a transition. So at every step you take, you just need to add a small value. And in essence, you just need to add like the difference of these two values because you look at the ratio. And then a nice thing is that you can actually, through Bayes, you can interpret this as a posterior quantity, right? As like the posterior, like the ratio of the conditional and the unconditional likelihood is nothing else than like the posterior quantity, which is very nice because at that point, like the Markov chain kind of drops out because you can rely on the Markov assumptions. Basically, that's kind of the rest of the trajectory, kind of the dependency drops out, and you solely depend on the current state of the objects, if you want.
That intuition, that intuition is that higher noise levels of an image cannot give you any more information concerning the class than the lowest noise level that you have available.
Yeah, exactly right. That's very well phrased. Yeah, that's the essence of the Markov assumption in a way. Okay, and so now the nice thing with diffusion models is that we kind of choose a specific parameterization for these transitions. That's the entire point. We choose them to be Gaussian, so we can just insert like our learned score functions or learned Gaussians into these approximations, and basically that way you obtain like a way of just through inference you can track this quantity just relying on your approximations of the conditional and unconditional score functions, which you anyway compute if you use guidance, then you anyway have these available, right? So it really comes at no cost at all if you use guidance, which people do in practice. So maybe to explain it like more visually or more like intuitively, the idea is that like at every time step, you are actually going to look at how well the conditional model works and compare that to how well the conditional model works. So what I mean with this is imagine that you're at time step t and you go to the next time step, so to time step t minus 1, you're going to look at how far that prediction is from the conditional mean and how far that conditional and so how far that prediction is from the unconditional prediction. And the intuition is that imagine that the next time step is very far from what the conditional model was predicting, then most likely you're currently not generating the condition because otherwise they would have been very close together. You would have been pointing in that direction anyway. Whereas if they're very close together, actually you get a very good approximation of, you really get a good information about the class you're currently generating. So that's really the idea. Like at every time step, you look at where you're going and you compare that to the two models, and you see like basically how much better does the conditional model work than the unconditional model. And if the conditional model works very well, then that means that your posterior should probably increase because you're generating the class. And if the unconditional model works much better than the conditional model, that means that you're probably not generating the condition C, meaning that the posterior should decrease. So that's really kind of the interpretation of it. Now, there's actually a subtle flaw or like some kind of self-reference in this equation when you use it for guidance. And the problem is that essentially at the beginning, you're going to sample using that conditional prediction. So in a way, you're kind of evaluating the performance of the conditional model on its own trajectory. So you're kind of sampling along that mean, and then you're asking it how close it was to that mean in a way. And obviously then it's going to think that it's very good at denoising that image, but it's really just because that's the best you have at that time step. You need to walk along the conditional mean, but that means that obviously the conditional model thinks it's doing very well, doing much better than the unconditional one, but it's just because it's kind of a bias that you have to live with. You're just evaluating how good it is at denoising its own trajectory, which it's obviously thinks that it's very great at doing, but that's really not what you want to capture. So that's why we kind of add an additional nudge to kind of help the unconditional model kind of also get attention, to also be seen as relevant, as not completely off. And in essence, that means like kind of adding this linear transformation, which can also be seen as a time-dependent prior, where we really try to kind of reinforce that okay, it might seem that the conditional model is doing much better, but that's simply because we're evaluating it on its own prediction. That's kind of what we want to argue with this linear transformation, and to make sure that the unconditional model also gets seen as relevant in a way. So that's a really important part of the approach, because otherwise you would basically just never obtain guidance. What you would have is that the posterior would just increase straight away and you would just never activate guidance. But that's just because you would be like asking an erroneous question in a way. So yeah, that's a really important part of this work. Okay, but I think now I've kind of introduced all of these tools. So I've shown how you can estimate the log likelihoods from the knowledge of the scores. I've shown how the guidance scale depends on this posterior likelihoods, and how that can affect and now let's look at how this can actually affect the whole sampling process. So for that, we're actually, and also I'm going to explain why we actually decided to call it feedback guidance, because I must imagine that for the moment it's probably not clear to you guys why it's called feedback guidance. And for that, we're actually going to make a connection with control diagrams. And so for this, we're actually going to see diffusion models in the terms of really a control diagram, with this idea that you have a state space and you kind of denoise it iteratively, and then you kind of loop around. You would kind of unroll this diagram if you want, and so you would compute the scores, take a step, mix the scores, take a step, and so on and so on and so on, until you get a very clean denoised image. So in the case of classify free guidance, this would just happen as such. You would unroll it just sequentially, so you would have lots of small steps basically, and you would just have this constant guidance scale. And so here the prompt is a chameleon blending into a graffiti covered wall, which is kind of a difficult thing to do. So a high guidance scale can be chosen. But what we argue is that imagine that you do the same thing. So you still apply a constant guidance, but now you try to do it for the Starry Night of Van Gogh, which the model has seen very often, right? It's really seen that prompt, so it really knows where to go. At that point, if you really apply the same amount of guidance, what you will see happening is that you really get this kind of saturation of colors, saturation of looks, just because at that point the model didn't really need guidance, but you still applied it because it just couldn't. There's no way for the model to not apply it without like any external information. And so that's really where our idea of feedback guidance comes in, is that there should actually be a feedback connection that at every time step evaluates the quality of your predictions and updates the guidance scale accordingly. So the idea is that once you've taken a step, you first take a time and you try to analyze whether what you're doing is good or not. And if it's very good, then you don't need to have that much guidance. But if it's very poor, then you should definitely add some guidance at the next time step. And in that way, you have a kind of feedback connection that allows for this guidance scale to be regulated dynamically throughout the denoising process. And obviously, this happens through the equations that we just proposed. So, yeah, go ahead.
Interject a moment. I just wanted to give I feel it's kind of the difference in which if your children on average misbehave after dinner, it's the difference between punishing if they actually misbehave or punishing them by default after dinner, because that's the region where they usually misbehave, And obviously the second wouldn't be a very good parenting strategy, right?
Yeah. I'm not an expert on that, so I don't think I can comment.
Okay, 3 of them.
But indeed, that's the thing. You really need to self-evaluate. You need to self-reflect, right? And I think for the denoising process, it's the same. It needs to kind of, if it's already doing a good job, then you don't need to alter it that much. You only need to change it if it's actually not doing a good job. That's really the main point. And so obviously this happens through the equation that we just derived above. So that means evaluating the quality is updating this posterior with as idea that if the posterior is high, that means a high quality, and the posterior being low is a low quality. And then we update the guidance scale accordingly with the equation that's we have with this dependence of the posterior and the guidance scale. And so in practice, let's look at how that would look like for our 2 prompts. So here, let's first look at what would happen in the case of the Starry Night. So what you would happen is that you would see that the guidance scale, so here it's plotted a bit small, sorry, but it's in violet. What you see is that actually during the denoising, quite early on, it would realize that actually, oh, I know what I'm doing. I'm supposed to do the Starry Night, which it knows. It's seen that plenty of times. Then at that point, the guidance scale will quickly decrease and you will just end up not applying that much guidance at all. Which is really what you wanted to do because it kind of eliminates this saturation effect and this really overemphasized look. Whereas, let's look at the case of this chameleon. What you would see happening there is that you would get much stronger guidance just because in the beginning it would realize that it still does not really know where it's going. It doesn't realize what it should be doing just because it's a much more complex prompt to kind of unravel. And so the guidance scale would be much higher. It would actually, like the posterior likelihood would go down and the guidance scale would go up accordingly. And in that way, you would have a much higher guidance. So yeah, so this is really a cool thing where like for the same hyperparameters, you really have this very different behavior depending on the prompt and on the trajectory even. So that's really the main idea of feedback guidance, is you should really evaluate how well your model is doing, and based on that information, you should apply guidance. That's really the idea. Yeah.
Question. Could you go? Because how does a Starry Night look like when you don't apply guidance?
Okay, yeah, that's a good question. I don't have that on the slide here, so I don't think that I can show you. But essentially, how it looks like it looks like the Starry Night. Like anyone would be able to recognize it. That's for sure. But what we notice is that most of the let's say really low frequency features, such as like for example like vivid colors, they tend to be missing if you just sample purely conditionally. So it kind of looks like, let's say with like low lights, Starry Nights with like not this really sharp blue that you would kind of expect from the Van Gogh painting. So yeah, in practice, purely sampling the conditional is not really exactly what you want to be doing either. So in essence, but that's a nice property of our guidance scheme, is that it can easily be combined with other schemes. So typically we find it actually beneficial in the case of text to image to kind of add a baseline of classifier-free guidance, like just a bit, just to get the low frequency details right. So just to make sure that you actually do kind of have these nice colors and so on, but not too high as to really destroy kind of the diversity of your model in a way. But it's true that if you just sample the conditional model, it's still not going to be exactly there. But it's clearly something that's memorized in a way. But it's a very good question.
And if you do normal classifier-free guidance, it'll be too saturated.
Exactly. Yeah. Yeah. Exactly. So it depends on the guidance value you use, right? So that's the thing. Like, for instance, if you use a low guidance scale value, then you might get a very good-looking images. But if you do that with the same level for this very complex prompts, then you will not get anything at all, right? You need a much higher guidance scale for the complex prompts than for the easy prompts. And so that's why we think that it's really not a good hyperparameter, because it needs to be like prompt specific and you need to choose it like accordingly as well. So our idea is that our approach should do that automatically. It should realize that this prompt requires much more guidance than the other one. That's kind of the idea. Okay. Maybe now we can, now that we've kind of been through the theory, that we've had this diagram of feedback guidance, we can take a look at how it works in practice. So in practice, we tested it out on ImageNet using the EDM2 models, which are excellent, which I highly recommend using. And there we noticed that it really drastically outperforms classifier-free guidance. And we also observed that it's very competitive with like the limited interval guidance work I mentioned, which just doesn't apply guidance at all time steps, but solely in the limited interval region in the middle. But I think like from the figure that I show here, where you see like our guidance profiles that are really dynamic and that change a lot compared to like their fixed profile, you can really see that they do kind of different things. So what you can really understand, I feel like from this figure, is that really hybrid approaches will definitely be very promising, and that kind of combining both, because that's just essentially they're just considering a different error assumption, and that can definitely be that case can definitely be argued. And just combining these two that behave very differently will definitely result in an improvement of metrics such as the FID and so on. Yeah, I added the table because it needs to be there, but I'm not the strongest believer in all of these metrics, and we notice that they behave very differently, and depending on what embedding space you use, and so yeah, but we still even on these metrics we're very competitive with the limited interval guidance work.
Can elaborate a bit, but so one thing is that just I mean that's a story a bit for future talks, but what we find is that for FID optimization on ImageNet, guidance is almost not needed. So it's guidance is almost a refinement, while for this FD Dino, that seems from recent papers to actually give better alignment with human perception, guidance is really required. And that's why it's actually quite difficult to make the dynamic guidance formula to work particularly well in ImageNet for FID optimization, because essentially the guidance formula wants to apply guidance when it has an effect, so when the semantic decision is made, but it actually is not the best thing for FID, because FID it uses a lesser trained network than Dino, and what's happened is that it often look at diversity, it really want to get diversity there, but sometimes the diversity is bad diversity, because it's diversity of things that they look diverse, but they don't look like objects. They look something that looks kind of like an object. So the case of FIE optimization in ImageNet is a bit pathological or peculiar in our experience. That's why I need to be careful with this kind of things. I think we will discuss this topic in the future more. Yeah. One thing I wanted to add about the hybrid cases is that I think you can still go a bit with the parenting metaphor. Is that if your children tend to misbehave after dinner, you probably want to be a bit more strict after dinner by default. The problem with a completely dynamic approach is that you need to have a very good reading of the situation, and that's statistically there is a level of efficiency that you need. This average guidance requires much less data to be estimated than trajectory specific guidance. So the bit of a strategy of getting a bit stricter after dinner, it's a good starting point, and then you can want to apply feedback on the top of it, you know. Which I think is a bit of the intuition that I sometimes, especially for badly trained prompt, it's just good to have a bit of a base level of guidance and then correct on the top.
I just have like a random question. It looks like if you take integral of this area under these curves, they look like maybe they could be the same. I don't know whether that has any meaning. It's just that.
Yeah. No, it's true that there are some work that consider this like kind of to be the relevant parameter, to be like, if you want, that's what you're referring to is the average amount of guidance applied, in a way. And I mean, if you divide it by the amount of diffusion steps, at least. And indeed, that's kind of a relevant quantity. You can understand it as like a level of guidance that the model applies. So that might indeed be in the future a valid hyperparameter to look at. Obviously it's difficult. You don't have access to that during inference, but it's clear that there's a connection on like the amount of guidance needed. Like all of these methods try to kind of apply the same final amount of guidance, because that's kind of how much guidance is needed. If that kind of makes sense on an average base, at least, but still they do it in very different ways.
Just need to be careful that guidance at different time points can do decently different things. So looking at the average level, it tells you something, but often the metaphor I give is that imagine that you're driving in a highway. Sometimes going to a class is like taking the correct exit, and it's not much about the average level of how much you're steering left, you know. because steering left in most places make you go somewhere else or crashing against the guardrails. So it's really sometimes it's really about steering left at the correct exit point. Actually, in the case of diffusion for kind of discrete, simple discrete models, you can see clearly that there will be very clearly demarcated exit point, what we call symmetry breaking point. For images, obviously, we not find these clear discrete sequences, but still, it's a lot about when you apply guidance. Because, for example, the decision between if the model is started to generate, is supposed to generate a cat, is start to generate a dog, the separation between cat and dog happens at different time to the separation between cat and chameleon, for example. And therefore, guidance at a different time has quite a different effect. So again, it's not just about the average; it's also about when the guidance has been delivered.
Yeah, I think that's a good point. It's really not only about that. It's really also about like when it's active and when it happens. And I think that's really an advantage of our approach. Is it kind of tries to estimate like when it's actually needed, and that means that it's really like, for example, in the example of the highway, like our approach should recognize that it should take the next exit, and then at that point it will start adding the steering to the left components to make sure that you actually take that exit. That's kind of the idea of our dynamic approach. But still, like, for example, base features such as like pushing on the gas pedal on the highway, that's something that you could add regardless of what you're doing. So they do different things, and they can definitely be combined. And we really think that that's a promising track for future work. Okay, and maybe so to reiterate on like I would like to highlight two of the kind of main differences of feedback guidance with more typical, like for instance, classifier-free guidance regimes. So the first one I would like to highlight is that our feedback guidance is really prompt dependent. So for the same set of hyperparameters, our method behaves very differently depending on the prompt you give it. So for instance, in the case of a very well-learned prompt, such as the Starry Night, which is even kind of memorized in a way, we really get very low guidance. So the guidance scale really does not go that high. Whereas for much more complex prompts, such as this chameleon in front of a graffiti, we really get much more guidance. We really get a much more dynamical system that really goes up much more drastically, which is expected intuitively. And so to analyze this a bit more rigorously, we designed a small scale data set of 60 prompts that are divided into 4 categories of difficulty levels. So we have memorized prompts. So those include, like, for instance, very famous places like the Taj Mahal or these paintings, such as the Starry Night. Then more basic prompts, such as, I don't know, a cat sitting on a couch, which is something that's definitely been seen very often. And then we have also intermediate prompts and like very hard prompts that contain like, I don't know, a giraffe playing basketball with 2 zebras running in the background, eating a hamburger. And you just have like a very difficult thing to generate, right? And what we observe is that our method really does give more guidance on average to these hard prompts than it does to the easy ones, which we really think is a very promising sign of the approach. It definitely shows that some part of the signal is definitely being picked up by what we do. And then the second kind of subtlety that I would like to highlight is that our feedback guidance, even for the same prompts, can really behave differently depending on the trajectory. And so what we didn't quantify this really, but like our observation is that it seems that when the conditional model was already good enough because that trajectory happened to be a good one for one reason or another, then the guidance actually is lower than in the other case. And so, for example, here, so the prompt was a snail on a leaf with water droplets. And I think you can, like, if I had just given you the conditional model predictions, you might have been able to guess it. It still looks somewhat similar. So like there's definitely some part of the signal that's contained in there. And in those cases, our guidance scale is lower. Whereas in the case of really very poor conditional model predictions, such as these two. Like if I had given you these two, there's no way that any of you would have ever guessed that it's a snail on a leaf, I believe. Or maybe you're really good at deciphering diffusion images. But the point is, if the conditional model prediction was kind of poor, then our guidance picks up on that signal and really gives much more guidance to try to steer them much more, because it understands that that trajectory is not going really in the right way. So that's really another kind of subtlety that our approach has, that really a base guidance method of just applying a constant global thing really does not have, and really think that that's valuable in a way. Okay, so now I've kind of done the talk, and I've arrived at the conclusion. So I'll just like reiterate on what we've shown here, and what I think are the main takeaways that I hope that you'll remember. So the first is that we have this new interpretation of guidance equations through error assumptions. And I think that's one of the really most important parts, actually, because it really allows everyone to come up with like a better error assumption model and straight away get a guidance methods for it and see how it behaves. And I think that's really a step forward to kind of understand why guidance is needed. The reason guidance is needed is because the conditional model is bad. So we just assume like how bad it is, how that error looks like. And I think that's really an important point. So I really want to emphasize that. And then we also show that adding this additive error, which gives non-zero likelihoods to like out of the conditional distribution, really results in this state-time dependent guidance scale, which we call feedback guidance. And we find that this feedback guidance is, first of all, like as expected, only active like in the middle in these semantic content generating regions of diffusion, just as limited interval guidance. We find that it's higher for complex prompts than for easier ones, as expected. And we also find visually that it's higher for actually poor trajectories than for good ones. So if the model happened to be on a good trajectory, our feedback guidance will not affect it that much. And last but not leastly, it's also really easily combinable with other guidance schemes that really do completely different things. And it's really think that hybrid methods are definitely the way to go in the future, and finding smart ways to combine them is definitely a very promising approach. Okay. So that was it. So thank you for listening. And yeah, if you want to have a further discussion, we can definitely talk.
Thank you for a really nice talk. Are there any questions?
Because you said it's in the middle of diffusion, but do the peaks overlap between between different prompts?
That's it. That's a very good question. So yeah, so in the case of image nets, so where you really have this class conditional signal, there they really do. And I think the reason for that is that there, like the images are always kind of in the same, like from the spectral perspective, they're really all like very well centered, kind of have an object in the middle and have kind of the same frequencies. Whereas in the case of text to image, it's more complex. So we really see that it does point sometimes a bit later, sometimes a bit earlier. But obviously, like we kind of try to make sure that it's within some kind of range. But so there's definitely some kind of different moments when it activates. So for instance, if you're asking for like a really low frequency image, such as the view of mountains in the background, and you just ask for that with nothing in the foreground, then the guidance scale will be much more active early on than if you ask for really like sharp details that are present much later on. So, but yeah, the way we set the hyperparameters, we kind of specify a bit the region where we want it to be, because we kind of know where it should be active to obtain like performance competitive results. So we kind of said that, but it would be indeed very cool to have something that's where the peak can really be move much more. That's a very good question. But yeah, for that really, I think that there's a big distinction between like class conditional generation and text to image. I think in text to image that's much more present than in class conditional.
I mean, I think you should be able to see that in class conditional, especially if you have classes that have a very clear background effect, like sharks, for example. I think probably will happen quite earlier because there's this expected value effect that just want to inject blue. So that could be interesting to investigate.
Yeah.
Also, that's a bit things that, related to other works we've been doing here, right? But the expectation of the log guidance, that should be quite directly an entropy rate measure, right?
Expectation of
lambda. So we have this lambda. If you look at log lambda.
Do you want me to go to the equation maybe?
It would be nice. So
there.
Here, yeah. So this.
So especially if you look at the bottom. So you want to take the expectation with respect to this, right? Of the log of that, and then basically you will get the conditional entropies.
Yeah, it's pretty much applied, right?
So it would be exactly. So that's for other people watching. That may be a bit mysterious, but we have been doing a lot of work for a kind of estimating the average kind of ways to apply guidance based on this entropy curve. So basically, and by the entropy I mean the entropy of this classifier, right? Imagine that you're sampling the trajectory and you're constantly looking, okay, is this a dog or a cat or is a shark? And then you can look at the entropy of the classifier and you can establish the entropy rate of the classifier, and basically some time points are associated with very high entropy rate, meaning that the decision about a specific class has been made mostly in that time point. And so essentially you want to look at the conditional entropy of the class given the current state X. And basically, if you take the log of lambda and you take the expectation over X, because then you take the expectation over X because you don't, for entropy calculation, you don't want to be specific of trajectory. You want to look on average at a given time point. And then I guess we get something very close to the entropy rate, right?
Yes.
But you have this difference.
Yeah, so that would not be exactly. So there would be something different, but at least we can relate it quite directly, I think.
Yeah, I think there's definitely some information to be retrieved from like even from the derivative of this guidance scale. If it can probably, as you say, be expressed in terms of entropy rates, and that's definitely an important signal. Like if it starts changing quite a bit, if it decreases quite a bit, that means that's the moment where signal needs to be injected in a way. If you really had a perfect system, so that it definitely should be rewritable as in terms of like information theoretic quantities, I believe. There's definitely a way to do that.
Yeah, exactly. It's not going to be exactly the entropy rate due to the difference, due to the fact that we're using kind of the wrong model, right? So there is the linear mix there, but we should be able to write it in terms of A in entropy, which I think would be insightful.
I mean, if you go to your muse, like going backwards on like likelihood and having the difference of muse.
Yeah. This one? Or?
But with muse, like where we can say mu.
The update formula. So.
Yeah. Like,
these ones? Or?
Yeah.
So that's directly.
Yeah, I think if you play with it, you will get some cancellations, but you will also get conditional entropy rate production because you will have like difference of two norms.
Yeah.
And then you will have also like inner product of xt minus 1 and like with the difference of these two, which is a new term. Which that's something new.
Yeah, so that would be interesting maybe to do in the future for relating a bit with because on this we have been doing like with the Jean, maybe it would be one of the next presentations, but we've been doing a lot of work for the entropy rate and also with Florian. So that could be nice to connect these two things and just studying the information theory of these dynamic guidance formulas.
Any other questions? I have one question. So
Okay.
you assume that your unconditional model is, like in your theoretical derivations, you assume that your unconditional model is correct, is like the perfect one, right? So, but in the literature, like they use also like badly, like smaller models that are not right. I would assume that are worse than the correct one, and that they show that actually smaller models give better results than using the larger models, which are probably better at learning the probability distribution. Like, do you have any idea why and how does it?
Yeah, so I think you're referring probably to the auto guidance paper that had like a best paper at NeurIPS last year, and actually, in fact, it's even very nice because from our framework, it can like be interchanged very easily. So in that case, what you would just assume is instead of trying to remove a bit of like the learn conditional, you just need to remove a bit of like even a worse conditional so that you kind of remove some of the errors as well that are in there. Some of the regions that might not even be unconditional that just happen to be there because actually the model learned something completely wrong there. And you just need to remove a bit of that. So like in our framework is really easily interchangeable with that. You just need to replace this one, let's say, this learned conditional by this poorly approximated object that might contain really artifact regions, let's say, and that's kind of the point of their paper.
The implicit assumption is that basically that the unconditional model trains kind of faster than the conditional one, and which makes sense because the unconditional is trained more. So that will imply that some of the artifacts that are already being solved in the conditional model are still there in the unconditional model are still there in the conditional one, which could be nice to actually try to analyze a bit theoretically this kind of things. Or yeah, I think that this framing that in terms of the error like this really kind of open to actually understanding instead of being a magic formula. And I think that still most people, when you talk about guidance, especially people who have a bit theoretical mind, they treat guidance as a magic formula. And I really like that, yeah, that with this approach we can start to make sense of what this formula means, how to derive other formulas, how to change our assumptions, like in this case, right? So I think it's quite insightful.
Okay. Yeah.
Okay, yeah, but thanks for having me. It was a great discussion with you guys. So thank you.
Yeah, thank you for
you very much.
coming. Yeah.
I'll stop the presentation. Okay, but see you all later. Bye.